Hello everyone. So this is experiment number 14, factors affecting reaction rate. There are 5 major factors that affect the rate of a chemical reaction. So number 1 is the nature of reactant. For a similar reaction, what is in the reaction? What is the reactants that are in there? That will have an impact to the rate of chemical reaction. Or for the same reactant, in what state it is. Usually gases react faster than liquids, liquids react faster than solid, and in a solution, ions react even faster. Well, today we're going to explore that, not all of them. Okay, we're going to do this, we're going to talk about it more when we start that section. Then the concentration of the reactants. How many particles are there in the reaction system? The more particles you have, the higher the concentration, the faster the reaction. Okay? For our solid reactant, what is the surface area? That can have an impact to the reaction rate. Okay? Only the particles on the surface of a solid reactant can react. Particles inside cannot react. So the greater the surface area, the faster the reaction. Reaction temperature. Okay? Now you know that for particles to react, they have to collide. They have to get into contact to each other. When temperature goes higher, particles move faster. When they move faster, they collide more often. They collide harder. Harder collisions can overcome the activation energy, resulting in a faster chemical reaction. And the last one, catalyst can lower the activation energy. When the activation energy of a reaction is lowered, more collisions can overcome that energy. That results in a faster chemical reaction. All right, now this is the first part of this experiment, nature of the reactants. And there are 2 sections that talk about nature of reactants. The first one, we're gonna use magnesium strips. Okay, pieces of magnesium strips to react with 5 different acids. Okay, we have sulfuric acid, hydrochloric acid, nitric acid, phosphoric acid, and acetic acid. Whenever you have to operate on acids, bases, or other corrosive chemicals in the lab, make sure you have to wear gloves. Okay, so what we're going to do in this first part is we're going to add 1 milliliter of an acid to a test tube. So 5 acids, 5 test tubes. Okay? And to each test tube, we're going to add 1 piece of this magnesium ribbon. Okay, they're pre-cut for us. They're about the same size. Then we're going to observe the reaction to see which one reacts faster. Well, how can we do that? If these acids react with their magnesium, hydrogen gas will be produced. Hydrogen gas will be produced from a solution. Then what you see bubbles coming out from. So what do? We're going to observe the rate of the bubbles to just eyeballing which one reacts faster. Okay, I'm going to add 1 ml of the acid to each test tube. Now I have 5 test tubes. Each one have 1 ml of the corresponding acid. So starting from the first one, sulfuric acid, hydrochloric acid, nitric acid, phosphoric acid, and acetic acid. Now I'm going to add a piece of magnesium ribbon to each one of them, and I'm going to show you the reaction rate. We'll watch them together. Look at that. Look at that. Okay. It's so hard for me to decide for the first 3. It's so hard for me. Oh, it looks like the first one reacts faster. Second one, third one, they're all gone, okay? Okay, they react so fast. These two, all the magnesium are gone. These two are still reacting. Okay. All right, so looks like number 5 is actually reacting faster than number 4. Okay, so let me tell you what I observe. The first 3, sulfuric acid, hydrochloric acid, nitric acid, the reaction rates are so fast. It's so hard to tell which one goes faster. I would say number 1, sulfuric acid, goes a little faster, followed by number 2 and number 3. Okay? Acetic acid actually reacted faster than the phosphoric acid. Okay? So here is the reaction rate sequence. 3M sulfuric acid, the fastest. 6M HCl, the second. 6M nitric acid, the third. 6M acetic acid, number 4. And 2M phosphoric acid, number 5. Okay? All other 4 are done. This is number 4, phosphoric acid. It is still reactive. Okay? Still there's magnesium in it. All the other 4, the magnesium pieces are gone. They're all done. Here is the second part. So in the last section, we used different acids to react with the same magnesium metal, magnesium ribbon. Now this experiment, this part, we are going to use the same acid. I have put 6M hydrochloric acid, 1 ml of that to each of these 3 test tubes. To each of these test tubes, I'm going to add different metals. I have, I have 3 metal pieces, magnesium, zinc, and copper. Okay, I'm gonna put them in and let you observe which one reacts faster. Copper. There's no bubbles. There's no reaction at all. Zinc. Oh, we see bubbles. Okay, bubblings come out. I'm going to leave it here. I'm going to put magnesium in. We actually observed the magnesium a few minutes ago. Oh, look at that. Magnesium, zinc. Okay, magnesium, zinc, and copper. No reaction at all. So the reaction rate of this part, magnesium reacts fastest, zinc the second, copper, no reaction. So in the experiment, we are going to monitor the production of iodine. When you mix these two together in a container, they react. When this one is used up, the iodide will react with iodate to produce iodine. In other words, when the iodine is produced, you know the hydrogen bisulfite is totally consumed. Okay? That reaction is done, it's finished. Okay, we monitor the appearance of iodine. Once iodine is produced, we know that one is used up, reaction is done. Well, how do we know if iodine is produced in the reaction system? How do we know that? Well, in the reaction system, we add starch to it too. Once iodine is produced in the system, iodine will combine with starch, and that complex, when they combine each other, that substance is going to show a blue color. So mix these two together. Once blue color shows up, you know, okay, hydrogen bisulfite, hydrogen sulfide is used up. So when you mix them together, you will monitor the system. When the blue color shows up, hydrogen sulfide is used up. So in this experiment, we are going to perform 3 separate reactions. Each one of these will use the same amount of hydrogen sulfide. We will alter the concentration of iodate. We're going to alter the concentration of the iodate in the reaction, okay, to see which one the blue color will show up faster. So basically, we explore the concentration change of the iodate, how that impacts the reaction rate. This is how we're going to perform this experiment. We are going to have 2 beakers. In beaker A, we are going to make a solution that contains potassium iodate and starch. In container B, beaker B, we're going to make a solution that contains sodium bisulfite. Then we're going to mix them together. We're going to pour them into a 3rd beaker. Right after that, I'm going to start my stopwatch. And then I'm going to watch the solution here. Wait for the blue color to appear. Once it appears, I'm going to stop the stopwatch and take a record of the time it used. Okay, the 3 solutions, 3 trials we're going to make. The mixture of different solutions, different concentrations are provided in the lab manual. Okay, I'm just going to go with that. Okay, we're going to perform 3 different reactions. Each time we alter the concentration of potassium iodate. Now there's one question need to be answered before we move on. Okay, to stop when I see blue color, I stop. That's fine. But however, I know that the blue color actually starts from very faint light blue and goes very deep dark navy. So when do I stop? Okay, theoretically, you can stop at any kind of blue as long as for the 3 trials, you stop your stopwatch at the same kind of blue. But that is so hard to do when you stop at the dark navy. You don't know what kind of navy it is anymore. So what I'm going to do here is, whenever I see any kind of blue, as long as the blue appears, I stop my watch. And I will do that for the same 3 trials. All right, now I'm going to start. So first, I'm going to measure 2 ml of potassium iodide. To this beaker B, we need 5 ml of sodium bisulfite. Now I'm going to add other components to beaker and A and B. Now solution A and solution B, they are ready. I'm going to pour them into a 3rd beaker. I'm going to start my stopwatch, and I put a white paper at the bottom so that I can see the blue color comes up clearly. Okay? Yep, I see blue. Okay, it's going to get darker and darker. Okay, again, when I see blue, I stop. I don't want to wait. It gets darker so that it becomes harder to predict what kind of blue it is. So, all right, it took 8 minutes 44 seconds. 8 minutes 44 seconds for trial 1. Okay, let's move down to trial number 2. Trial number 2, the amount of potassium iodide is 4 mL now. 4 milliliter doubles the concentration of potassium iodide in the first trial. I'm going to pour them together and start the stopwatch. Blue. All right. 4 minutes and 4 seconds. 4 minutes, 4 seconds. The one before was 8 minutes, 44 seconds. This one's 4 minutes, 4 seconds. This was the first one now, second one. Now let's move on to the third one. The third trial, the concentration of potassium iodide tripled from the first one. So we expect the reaction rate is even faster. Hopefully it takes even shorter time before we see the blue color shows up. blue. All right. 2 minutes, 53 seconds. 2 minutes, 53. Okay, so you need to take a record of the the times used for the 3 trials. 8, 44, 4, 4, and 2, 53. Now, surface area. We're going to use a reaction between marble chips, a marble chip, react with hydrochloric acid. So we pick 2 pieces of marble chips. They're about the same size. The book says around 15.05 gram, which is 15 milligrams. Mine, I just did a measurement. Roughly, they're about 100 milligrams each. So about the same size, okay? So one of them, I'm gonna let it react with acid as it is. The other one, I'm gonna put it into the mortar and pestle. I'm gonna grind it down to powders. Okay, now I'm gonna put this into the test tube, into these test tubes, and add acid, and we'll just eyeballing which one reacts faster. All right, I'm gonna add about 2 mils of hydrochloric acid to each one of this. First one goes to the chips. Second one goes to the powder. Wow, you see the difference right away. This is a chip, this is powder. Clearly shows us greater surface area. The reaction goes faster. Temperature impact. Now in this experiment, we'll use 3 test tubes. To each one, we are going to add 5 milliliter of 6M hydrochloric acid, and then one of them, we're going to place them into an ice bath. Temperature will be close to 0. Another one in a 50 degrees Celsius water bath. A third one in a 20 degrees Celsius water bath. Then we will put 1 piece of zinc strap to each one of them. I actually measured the mass of them. They're the same. They're all around 130 milligrams. Once we put them in, we're gonna start a stopwatch. We are going to take a record of the time it takes for each reaction and compare the 3 reaction times to see which one goes faster. All right, let's start with the temperature. The reaction at the highest temperature, the one that at 50 degrees Celsius, that one we expect it will react fast, the fastest. All right. All done. 38 seconds. Now let's look at the 20 degrees Celsius. The first one, 38 seconds. A little slower. A lot slower actually. All gone. All the zinc disappeared. 2 minutes, 35 seconds. 2 minutes, 35. The last one was 38 seconds. This one is 2 minutes, 35 seconds. Okay. 0 degrees Celsius. Pretty slow. So we'll leave it there. I'm going to prepare the next part, and we're going to come back to take a record of it. It's going to take some time. As we can see, it is very, very slow compared to the other two. It has been 8:30, 8 minutes 30 seconds. It's still there, still reacting. Little small piece of zinc on the top. Okay, still there. Don't know if you can see it. It is still there on the top. Oh, it's broken down. It's broken down. Still there. It's gone. Okay. It is all gone. 9 minutes, 16 seconds. 9 minutes, 16 seconds at 0 degrees Celsius. All right. Now, the last part of this lab, the impact of a catalyst to the reaction rate. The reaction we used is the decomposition of hydrogen peroxide. This is hydrogen peroxide. Hydrogen peroxide is not stable. It will decompose to produce water and oxygen. When oxygen is produced in the solution or in the liquid, you see bubbles coming out. So we will do 2 experiments. One, hydrogen peroxide by itself. 2, hydrogen peroxide with some catalyst added. The catalyst we use is manganese oxide. So let's take a look at the hydrogen peroxide by itself to see if you can observe any bubbles. Well, I can't. I don't know about you. I do not see any bubbles at all. So that tells you hydrogen peroxide is not decomposing itself, or the reaction may be so slow that we cannot observe the bubbles. So let's look at what will happen. This is hydrogen peroxide by itself. Let's look at what will happen if we add some catalyst. I don't need too much, just need a little bit. All right. This is how much I'm gonna add into it, just the tip of the spatula. The first one, number 1, the second one, number 2. I'm gonna add to number 2. Look at that. Look at the bubbles coming out from it. Okay? Now it's the difference. With the catalyst, hydrogen peroxide decomposes very fast. You see, now it is done. There's no bubbles anymore. All the hydrogen peroxide has decomposed. All right? Without a catalyst, with a catalyst. Take a record of what you observe, put it on your lab report sheet. All right, that's all for today's lab.